I'm very happy to introduce Professor Sylvain Cappell, who has been attending this seminar for a long time. I have
Decades.
no actual record. It's definitely decades, but I don't remember if it's been before I was born or not. Well, naturally. And I guess he is someone who really doesn't need an introduction, so I'll just let him speak.
Okay, thank you very much. So I'm going to give a little talk here about some questions that arose in graph theory in my joint work with Ed Miller, who's happily here and has helped not only with the work and the research, but also with kindly helping prepare the presentation here. So so we've been working on some things related to graphs and some matrices associated with graphs and their geometrical applications in several different directions. Okay, is it working?
It is.
Great. In several different directions. I'll mention some other directions, but I won't get to all of them today by any means. So among the other directions that we've been working, first of all, I'm going to be focusing on graphs, which is kind of the one-dimensional phenomena. But we also have papers dealing with analogous questions for cell complexes, for higher dimensional cells. And it'll turn out that some of the geometric combinatorics I'm discussing with have more complicated generalizations for cell complexes as well. And so we have some papers on that, and they're more complicated, the matrices that come in and the interpretation of the results. So I won't get into that. Today, I'm just going to talk about graphs and focus on that. Another series of papers we have, even in the context of graphs, is I'm going to be discussing two different matrices that come up when you study graphs. One is a very classical matrix, the Kirchhoff matrix, which every graph theorist has looked at, and there's a vast literature. When I say vast, I mean thousands of research papers, literally thousands, actually. But there's a second matrix which is of interest, which we call the mesh matrix. It was invented by a researcher named Trent in the middle of the last century. And it's a different way of getting a quite different matrix, different size matrix out of graphs. And it measures different properties of graphs. But as we'll see, it also has some analogous properties. In both cases, we're going to be interested in measuring something called spanning trees in graphs, which I'll explain what those are. And what we're going to be interested in discussing is ways to enumerate spanning trees. Now, studying spanning trees is a classical subject that goes back to Kirchhoff's work in the mid-19th century. And Kirchhoff defined this matrix from which, via a determinant type calculation, he could calculate the number of spanning trees. And it turns out that Trent proved that something similar happens with this other matrix, the mesh matrix, which I'll explain, and I'll explain geometrically what it is. As I say, it's a different size matrix, but again, out of it, by determinantal calculation, you can again, from this quite different matrix, calculate the number of spanning trees. And as I said, there's a vast literature about the eigenvalues of the Kirchhoff matrix. There doesn't seem to be a literature about the eigenvalues of the Trent matrix, but Ed and I have a paper on that, and on the geometrical interpretation, some of the results have parallel in a way, some of the results about the Kirchhoff matrix and its well-studied eigenvalues. But I'm not going to be talking about any of that or the high dimensional things. Instead, what I'll be focusing today is on a more narrow problem, which is how do you actually not just count the number of spanning trees in a graph, how do you actually enumerate the number of the set of spanning trees? And I will describe methods of enumerating that work with respect to both matrices, though qualitatively the kind of answers I get have a subtle difference between the Kirchhoff matrix and the mesh matrix, and I'll try to explain a little bit about that difference and how they both come in. Okay, so that's the plan over here. So that's by way of a survey of what I'm going to be trying to do. And the object is to, as I say, is to enumerate the spanning trees, but enumerate them in a way that's algebraically natural so that you can apply other methods. I mean, spanning trees apply in a lot of different contexts, ranging from chemistry to probability. And having a natural way to spin them or list them seems like it could be of real application in a number of directions. So that's our hope that motivates the present discussion. Okay? Any questions so far from this general Discussion? That's what's planned. Okay, so I need to go back to the beginning and remind you what we mean by a spanning tree. So G here is a finite graph with vertices, which are listed over there, and edges. The vertices are P1 through Pn, the edges are E1 through Em over there. And we're going to orient, sorry, okay, I did that wrong, hit the wrong button. We're going to orient the graph so that every edge is going to get every edge is going to get an initial vertex and a terminal vertex. And when we have an edge, the two vertices are said to be adjacent. And we'll also talk about the edge in the opposite direction, which is called minus that edge over there. And those will be the directed edges of the graph. Okay. And then a directed path in G from a vertex A to a vertex B consists of a sequence of these vertices with a sequence of directed edges connecting between them, okay? And a graph is connected if any two vertices can be connected by a path. Okay, now if the two vertices that you're getting at the end, you can always, directed vertices can be replaced by one with distinct vertices, giving a simple directed path from A to B so that you don't cross it through it many times and so on. If A equals B, the directed path is called closed or one cycle. So that means there's a loop coming all the way around. And one cycles can be decomposed into geometrically into simple one cycles, which have distinct vertices. So that's like a little circle here and a little circle somewhere else, and so on. An example is a loop, one edge, sorry, keep hitting buttons accidentally, one edge with both end endpoints the same. That would be an example. Okay, now let me see what happens when I hit this once. Okay, once, nothing happened. Okay, there. And now a tree. So in a graph, a tree, well, the name is very evocative of what this is. A graph is a graph which is connected and has no one cycles, no big loops coming around again at all. And you can construct a tree, for example, very easily by pick a vertex somewhere, has a root, and then you look at the vertices which it connects to, and then you look at the vertices that one connects to, and so on. And then you can construct, if you keep getting new vertices this way, so you don't get any loops, then you'll get what's called a tree inside a connected graph. And any connected graph has a tree in it. Any connected graph has a tree, and in fact, it has many trees that you could draw in it. And the object here is going to be, first of all, I'll recall in the course of this some classical theorems that count the number of such trees there are. The trees that you can form out of a graph that contain all the vertices are called the spanning trees. So I'm going to be counting the number of spanning trees, and then I'm going to also be developing methods using a certain algebraic framework in order to actually list all of them, actually. Now, let me say right at the very beginning that it's not, I don't want to claim that these results are shocking. They're not, in the following sense, that from a point of view of algebra or analysis, determinants, as I say, in both the Kirchhoff matrix context and in the mesh matrix context, we use determinants to calculate the number of spanning trees. Now, it's a very familiar fact to either algebraists or analysts that determinants are closely related to exterior algebras. Exterior algebras, which I'll describe what they are, and I'll recall, I'm not going to assume you know what an exterior algebra is, but I'll recall it. But exterior algebras are well known to give a very natural framework for constructing determinants and breaking up a determinant in various ways, corresponding to the way that the determinant is a sum with signs of various determinants and so on, of minors. And so it's kind of natural to think that the exterior algebra might be a way of getting more information out of the system than just the determinant. It'll give you the determinant and what lies behind the determinant, which will turn out to be a listing, in this case, of all the spanning trees. So that's going to be the strategy. Take advantage of the fact that determinants are closely related to exterior algebra, and then use the exterior algebra to actually get an expression for the actual spanning trees, a listing of them actually. And as I say, we'll do that in two different matrix contexts, quite different matrix contexts, with some differences between them actually. Okay, so that's the plan over here. So I think I already said we can connect each vertex to a root. We start off with a root in a graph, and then we can connect every vertex in a tree to it by just pointing towards the root. So we go towards the root, and as we go towards the root, we get an edge that's close. We get an edge, and then we end up at a vertex that's closer to the root, and we can keep going this way until we finally get to the root. We could use any vertex as the root of a tree and go that way. Okay. And here's again, sorry. For a T, a tree, which is subgraph or graph. Again, it's a spanning tree if it contains all the vertices of G, and our interest is in enumerating the spanning trees of G. Now, the picture that I just had on a moment ago suggests that given a connected graph with vertices which are listed with a chosen root, we can try and list one way to try and organize a spanning tree and describe it is by choosing a kind of dynamical system on the set of vertices where you have a function capital F that sends each vertex to a vertex that's closer to the root. So once you've got a tree at a root, you could just map each vertex to the next one by shrinking in along the tree. The tree, of course, itself, topologists can't help saying is null homotopic. You can shrink it to a point, and this dynamical system realizes that shrinking in towards some root that way. Okay, so here is a description of how you do that, and you can end up shrinking all this in that way when you have such a dynamical system. Okay, that way. And all spanning trees can be produced by such a process of pulling things in towards some root. Parenthetically, we'll note that the definition for the complete graph, so the complete graph is the graph of all possible edges between all the vertices, very filled-in graph, with n vertices, has a unique edge between any two vertices, and it's known to have n to the n minus 2 spanning trees. That's a very classical result about enumerating. So if I just pick a random kind of dynamical system, I could calculate the probability that I'm getting a tree out of that. And you can do some little probability calculation there, which is approximately E over N of the chances that I'm getting this. But now we want to actually describe an algebraic method, which actually picks out the spanning trees from this whole vast list of possibilities. And as I say, interestingly, exterior algebra is going to provide a very natural language in which to do that. So, what we're going to want is an algebraic method that takes any such f, and if it has one cycles to it, if it has loops, it's going to just give us 0, and they're not going to show up at the answer. But it's going to preserve things when we actually are producing an f, a dynamical system that converges on a tree. It gives us a tree, and those will get listed, and the others will disappear from the formulas magically. Okay, so that's the magical method which exterior algebra is going to allow us to do. That's the plan for this whole thing. And the exterior algebra I'm going to describe, so I'll explain what an exterior algebra is in a moment, but the exterior algebra starts with a vector space always, and then it produces a certain algebra out of that vector space. So the vector space that's going to be in use here is going to be in one of the treatments, in the Kirchhoff type treatment. The exterior algebra that I'm going to be using is going to be the exterior algebra built on the vector space of directed edges of the graph. So I take the directed edges of the graph and I produce a vector space of that dimension, actually, and that's going to be the vector space W. And from W, I'm going to produce a certain algebra, and then from that algebra, I'm going to get a list of the spanning trees. Okay, that's the plan.
So what did I take? So if the opposite you consider is
I'm sorry, what?
If two edges like opposite.
Yes, so I'm only counting them once. Oh,
or it's minus. I mean, what does it?
Yeah, so the edge going the opposite way is considered the minus of the edge going the other way here. Okay. Okay, so now I'm going to explain, first of all, what an exterior algebra is. So to begin with, I'll make an analogy here with polynomial algebras, which people are more familiar with, no doubt. Okay, so real polynomials on free variables means you've got a bunch of variables, x1, x2, and so on, of some of degree. Degree in a given degree, say they're all of degree 1 here, these variables, and then the degree d is given by sums of monomials of degree d in the variables, right? That's how you form polynomial algebras, of course. And here, life is easy. We're going to just think at the beginning about commuting variables. So these variables commute. That's how you do it in a polynomial algebra. And of course, when you have a polynomial algebra, you can write every polynomial as a unique sum of monomials times coefficients and so on. You could talk about monomials with a given total degree and only confine yourself to homogeneous polynomials that have a given total degree. And that's all familiar stuff in the context of polynomial algebras. Yes? Okay. Now I'm going to do the same thing in exterior algebras, but the exterior algebra is a little bit different. It has a sign in it here, which doesn't screw things up. It helps things, actually, it turns out. So in the exterior algebra, we again start with a bunch of variables, free variables. Let's call them again x1 through xn. And we're again going to form products and take the corresponding sums. But now, instead of having commuting relations, we're going to have anti-commuting relations. So when you have the eighth guy, x sub a, times x sub b, that's going to be minus x sub b times x sub a. So there's a sign switch over here. Now, this sign switch is very convenient for a lot of purposes in calculus on many variables. For example, calculus on manifolds. If you look in books on calculus on manifolds, they use this same sign convention also. Now, since you have the sign switch, that has certain implications. For example, when you take x sub a times x sub a, it's equal to its minus. Since we're working with real vector spaces, that means that it's equal to 0. So a symbol times itself, one of the monomials, one of the generators times itself is equal to 0. So when you have two occurrences in a string of the same x sub a, you're actually going to automatically get 0. And like in polynomial algebras, of course, you can reshuffle. Here also you can reshuffle, but you reshuffle at the cost of introducing signs, because each time you shuffle a pair of things, it introduces a -1 into the business. So it keeps track of how many times you're shuffling as you move things over. This will turn out to be useful from the point of view of determinants, because you may recall that the way determinants behave is the same way, that signs switch each time you reverse a column or a row. And so that's going to be why exterior algebra is so well tied to the notion of determinants, actually. Okay? So now you can again, and when you write the products in exterior algebra, to remind you that it's anti-commuting rather than commuting, you write it as this wedge over here, the product. It's conventional to write it as a wedge product like that. And however, you can again reassemble terms. You don't have any higher powers of terms, because we already said that x sub a squared, any of these terms alone, squared is 0. So unlike a polynomial algebra, which keeps growing the degrees all the way out to infinity, this stops by the time you got all degree d, the dimension of the number or the number of variables you have. You can't go above that, because you'd be repeating a term and then getting 0. Okay? And in fact, you get monomials of degree d, and the number of monomials of degree d is the combinatorial at the bottom of this page, n choose d, like that. That's the number of terms. So if you like, the exterior, so that's the homogeneous part of that's the size of the homogeneous part of the exterior algebra of degree d. If you add it all up, by the way, the degrees of the size of all of these, you're getting the sum of a row in Pascal's triangle. So you would get 2 to the d actually as the sum. So it stops at some finite point at dimension d. So that's why, in a way, exterior algebras, despite being anti-commutative rather than commutative, are easier. They're finite dimensional things as opposed to polynomial algebras. Okay? So that's part of what goes on here. Okay. Okay, now this is just a recalling here what the multiplication of monomials is. Just like in polynomial algebras, you put them together, but putting them together is written by this wedge. This wedge is associative, so there's no difficulty with that. And when you take things of degree A and you multiply them by things of degree B, you just get something of degree A plus B, like in the polynomial algebra. And then when you looked at these generators, x1, x2, I said when you reverse the order, you get a sign. But if you have polynomials which are of higher degree and you multiply them, there may or may not be a sign. It may be plus or minus. It depends how many switches there are as you as you move things over. So you actually get -1 to the a times b when you switch the order of multiplication of higher degree terms. Okay, so you might be plus, you might get minus when you multiply monomials that way. Okay. All right, so for example, there's some examples over here done there. For n equals 3, these are the symmetric forms. These are the symmetric free variables, skew symmetric free variables that you could get in degree 1, in degree 2, in degree 3, and so on. After degree 3, there are none for 3 variables, as we said. It's all finite dimensional. Now, let's briefly discuss how this is related to determinants. Okay, so determinants have the same kind of skew symmetry. So it's not hard to take it to see that these are related. And in particular, if M is an n by n matrix with entries, Aij over there, and you have a bunch of free variables generating your exterior algebra, then if you look at what the matrix A does to the variables xi here, so that's written this equation over here, over that sum over there, it describes how just expressing the matrix as a linear map from the variables to themselves and so on, then you get a nice equality which says that when you look at the highest dimensional degree term in the exterior algebra, so the highest dimensional term is an exterior, that's called exterior product, this wedge. It's going to be an exterior product of all the one-dimensional pieces put together. And so that's a degree, that's dimension 1, the highest term. By the way, there's a kind of duality here because it reflects the duality in combinatorics. When I choose I from n objects, that's the same as choosing n minus I from n objects. So the top dimension is the same as the bottom dimension 0, which is just the real numbers here. And so the top dimensional guy is just a single real, and it's generated by the product, the exterior product, x1, wedge x2, wedge x3, and so on, all the way to xn. And that, when you take a linear map, a matrix, and you try and see what does it do, not just on the vector space you started with, but on the whole exterior algebra, it turns out that the very top term, what it gives you is exactly the determinant. And that's because the way these things were cleverly arranged, they have the same sign changes the determinant do. And so actually you get an expression for the determinant this way from the exterior algebra by looking at the top exterior power, the top degree terms. So that's how the determinant is read off from the exterior algebra. That's the relationship between them. Make sense? Okay. All right, and this is useful in calculus because it provides a nice way of dealing with integration on manifolds or in multidimensional situations in general. You can assign, if you assign to each point P of a space a skew-symmetric multilinear map of the default product of the tangent space to the reals, you get something that's called a deform that way, and deforms are a good way of keeping track of what you're integrating over d-dimensional subspaces. They have the right sign conventions. The basic sign convention, of course, is that integrating from A to B is negative, integrating from B to A. That's built into this. Okay, anyway, you can do calculus this provides a very convenient language for doing calculus in multivariable settings, which one takes advantage of in discussing how to do calculus on manifolds like that. Okay, I think I was here. Yes. Okay. I'm not going to use that. I'm just mentioning it here that this is a familiar setting. Okay, so here is the first result we're going to be discussing. So let G be a connected, directed graph. So I pick some directions on the graph, whatever, and I have vertices, and I've chosen the direction for the edges over there, each edge, and I'm going to pick some vertex in the graph as my root, and I'll be constructing trees with that root. And again, we have the convention we mentioned before that minus an edge corresponds to the edge with the opposite orientation, the opposite direction on that edge. And then associate to each of the chosen directed edges, say EJ, a certain one, a free skew commuting variable. So that's something from which we can construct an exterior algebra, and also associate to the oppositely directed edge the negative of that variable. Okay, so you can think of that variable as being the edge itself if you want. Okay, in the exterior algebra, they're generated by these symbols, and these symbols correspond to the edges. That is, changing the direction again multiplies it by -1. And now let's let W1 through Wn minus 1 denote the n-1 elements of the set of vertices minus the root that I started with. So I'm looking at all the vertices other than the root over here. And I've ordered them in a certain way, increasing order, whatever, some lexicographical ordering that I've made. Now, introduce for each the mapping F. So F is going to be like what I was talking about before, kind of dynamical system. On the set of vertices, look at the map that sends each vertex, each of these vertices to the set of vertices. But I'm now going to look at the element of degree M of the exterior algebra now, the particular element. Sorry, I accidentally moved forward more than I meant to. Okay. Okay. So now let's look at a wedge product of all of the. So here I have these lexicographically ordered things, and now I'm looking at the wedge product that I get from these and their images here, which are the next things that I'm getting. And now I look at all of those over there, and I take that wedge product. And now the claim is that this sum that I get, this exterior product that I get this way, is going to be zero if and only if the dynamical system defined by F, as I move F along, is going to have a cycle in it. If it has a cycle in it, a loop, this is going to disappear in the exterior algebra. Whereas if I don't have a cycle in it, it's going to show up. It's going to turn out. So otherwise, in other words, F consists of the wedge product ordered by the initial vertex of the unique directed spanning tree of G directed inwards to the root VK. So all the spanning trees of G with their uniquely determined directions toward the chosen root will be enumerated and arise in this manner. Okay, so this is going to be, here's an example over here. This is a little triangle over here where I've got 3 vertices and 3 edges over here. And I've listed the vertices here, and the edges I'm forming exterior products. So V2 arrow to V1 represents an edge from V2 to V1 and so on. And then I'm listing here all these exterior products that I get out of this. And if I had any cycles here, I would get 0, it turns out. We'll see. And this is going to give me a listing of all from this exterior product. I'm going to get a listing of all the enumeration of all the spanning trees with a given root towards a given root. Now,
Sorry, I'm lost on the first
Please.
slide of the theorem. Can you please go back?
sure.
Sorry, this is very complicated. No, the first slide of the theorem.
This?
No, the previous one. And yeah, I think I've lost already here.
Yeah.
So first we take vertices,
Right.
and then just
I'm going to take an exterior product where I look at all of these possible edges here, and I'm going to take the wedge product of these things and add them up.
Here negative x 3 minus that. Here the exterior will be this changing direction relationally, but that's fine. And then when we double 1, we double 2.
Yes. Right.
This I don't understand. So what is VG minus VK? So we take vertices minus. What is minus here?
Set minus.
I said minus.
Yes.
So exclude.
You throw away the root,
I throw away the root.
and then if you have a function that says, and if you don't have a root, you decide where it should go. You get an edge, yes. Then you take the wedge product of the edges.
No. So we double 1, we double 2 is the vertex, right?
Vertices, it's
Yes.
the ones that are not the root.
Okay.
So this will be a sum of all possible choices there of these dynamical systems.
Okay. So
But the ones that give me loops will turn out not to contribute in the end. That's the claim. They're going to disappear from the sum that I'm getting. So I'm going to be writing, in other words, what I'm going to end up writing here is a large sum inside an exterior algebra. And each of the monomials that I get out of this is going to be, in fact, describe a tree directed towards the root.
Yeah, but I just don't.
And all the other terms will turn out to vanish.
Yeah, I just want to understand the construction. So what? Next slide, please.
Sure.
I just want to understand what.
So at the top, you see, you take a non-root root and you say, oh, I'll send it here. That's a dynamical system.
That doesn't have to send it to
A
respect
neighbor.
the edge or no? Does
You
F
could
have
say-
to respect the edge?
F sends the vertices not equal to the root to any vertex. It's just a map.
Doesn't have to be
anything, you
Okay.
take all of them. But then once you take all of them, you say, I'll send the first W to this one. That gives you an edge. And for the second one, you send second W to where it goes. So this F provides you with a listing of edges.
This dynamical system,
Yeah, there, so
you
there,
have this
you have this element.
linear algebra,
Yeah, you got it.
right?
And the claim is going to be that all the things that have loops in them will disappear in the sum that I'm writing down. And so I'll be left with a listing of all the spanning edges, actually that way,
So,
just out of the exterior algebra formalism.
again, why if you have a loop when
Okay, so that takes some discussion. So I think that's over here. And the proof logic comes down to showing that if F gives rise to a one cycle, if there is a one cycle somewhere in it, and it doesn't have to be the whole thing is a cycle, but if, for example, in this picture on the left here, you see there's a cycle going around over here in this little square. If there's a one cycle in it, then you get another term that comes up in this summand that also has the one cycle going the other way around as well. And happily, it turns out that those terms come up with different signs in the exterior algebra, and then they cancel off. So all the terms that have a one cycle in total appear 0 times, actually, automatically. No matter how big the cycle, doesn't matter. The parity, the size of the cycle doesn't matter. When you work out the signs, it turns out to be minus it, whether it's of size 3 or size 4 or whatever, actually. So when you do this calculation, everything wipes out to 0, and the only residue that's left in the formula is the spanning trees, remarkably. So that's the claim. Actually.
I think I don't understand the notation. But how, so each H is like kind of.
Well, for example,
Additional, it's a variable. So if all variables are different, how it can have a 0?
Well, remember the terms are being counted here. The terms can come up with a multiplicity. They can come up more than once, depending upon what happens. And in fact, what will happen is when there's a cycle, you're going to get the same term coming up 2 times with opposite signs automatically. So, for example, here's a picture that shows this, illustrates this. You see, here's a little blue square over there in that picture there, okay? So over here, the vertices are ordered. For example, there's vertex 5, vertex 6, vertex 7, and vertex 8, let's say. Those are the vertices. Then over here, I'm going to get out of this, following this around, I'm going to get the edge from V5 to V6. Then I'll get from V6 to V7, from V7 to V8, and from V8 back to V5. On the other hand, if I look at the square with this square, everything else left the same, but this little one cycle, this little blue square oriented the opposite way, right? What happens is going to be that from V5, I will have the edge going to V8 here. So I'll have the vertex V5 to V8. From V6, I'll have only the edge going to, with this orientation, from V6 to V5. From V7, I'll go to V6, and from V8, I'll go to V7. Now, when I look at this exterior product here, and I take account of the sign conventions. So remember, there are 2 signs coming into the sign conventions, because first of all, if I reverse the order of an edge, so it goes from A to B rather than B to A, that introduces a minus. And also a minus gets introduced because of the exterior algebra when I reverse the wedge product. So when I do, now when I calculate what the effect of both of those together is, I always end up with a negative of what I started with happily. And so it kills the terms that involve a loop automatically when you work that out, the signs out. Kind of amazingly, it kills those terms.
So you see that the first term on number 2 is put in the last term, get a -1 cubed. Right? Going from the first one.
Yeah, so it ends up in this case, by the time you measure the number of sign changes, you're getting -1 cubed. So the term with the addition with the opposite orientation is -1 at the end. And so it cancels off.
And all terms, you change the order. Which is -1 to the 4th.
Yeah. Okay.
And by luckily, right? Or opposite.
It's kind of a miracle, but it works. Okay. Okay. Now, there are various generalizations of what I just said. So over here, I talked about spanning trees with a given root. You can generalize this in a bunch of different ways. I'm just going to mention some of them There are a bunch of different generalizations. You could also talk about what are called spanning forests, where you connect them not just to one vertex, but to a bunch of vertices, and then you could have a theorem covering spanning forests rather than spanning trees. And maybe I won't bother with the details of that, but there's the analogous theorem works for spanning forests as well. You're using a different degree in the spanning forests and so on than you were in the exterior algebra for the spanning trees, but you get a similar formula and things cancel whenever there's a loop and so on. And so, and you get the remaining terms, as it says at the bottom of the slide, all terms not expanding forests rooted at V and J vanish. And the remaining terms that are not zero enumerate all the spanning forests rooted at the system J, actually. So this technique works not only for counting spanning trees, but also for counting spanning forests. Another direction of generalization is, well, okay, so this is yet, I don't know if I'll have time to say it, but there's also a generalization where you do measure weighted edges. You can look at graphs with weighted on the edge. That's in a lot of applications. And you can adapt everything I'm saying to a context of weighted edges as well, with the same exterior algebra formalism actually works there. But I don't know that I'll get time to run through any of that in detail. Now, now here's another direction in which this can go, which is the following. So suppose I pick a spanning tree of a connected graph with n vertices and m edges. It's a standard fact that for each connected graph has a spanning tree, just by picking out a big maximum that you can keep going. So there's this relationship between the number of vertices and the number of edges. And then you can look at the number of edges minus the number of edges in the tree. And if you pick a direction for them and those edges, and you consider their boundaries. Now, what you can get out of this is the following. Well, maybe I should just imagine as a topologist a picture here. So I have here a graph, which is a one-dimensional space, and I'm pulling out of it a spanning tree, which can be shrunk to a point from a topologist's point of view. So from a topologist's point of view, the one-dimensional homology, the loops that are left at when you shrink the tree to a point, are given by the edges that are outside the spanning tree. That's what I'm describing over here, that you take each edge outside of a spanning tree corresponds to a cycle that goes all the way around and forms a loop. So that's the Z1 over G here. That's the group of cycles over here, the one-dimensional cycles. And if you like, that's the kernel of the boundary map from the one-dimensional edges to the zero-dimensional edges. They can be described concretely in terms of the edges. You can give them a basis using the edges outside of the spanning tree, the complement of the spanning tree, okay? So that's what's going on over here. And, okay, so then I'm going to order these things outside the spanning tree, and I can form
I think you have to go a few pages now.
Sorry?
Your pages off.
I skipped it. Oh, I went wrong.
It's-
Okay, yeah. So over here, so I could look at the cycles over here that I formed by starting with an edge outside the spanning tree. That's sitting inside the set of all the sums of the edges, and then I can look at the cycles on the vertices of G minus the vertices of the tree, like that, and I capture everything, all the cycles, by knowing what's going on outside the spanning tree. So that's the statement that this linear map is an injection. So this gives it another way of characterizing spanning trees, and it's going to use the complement of the spanning trees instead of doing algebra on the spanning trees. So we are going to form a matrix which we call the mesh matrix. Maybe I better explain this not using matrix since our time is short. Let me explain this geometrically, what the mesh matrix is. So, and then I'll tell you what it is algebraically as well, without explaining that maybe all the details of why those are the same. But the mesh matrix is the following. Let's look at the one-dimensional loops inside my graph. So I look at the one-dimensional loops there, and it's natural to form a matrix that measures how many times do two such loops overlap with each other? How many times do they mesh together? So if I have two loops, for example, I'm going to measure how many of these edges they have in common. That's going to be called the mesh matrix. And in the definition of the mesh matrix, I keep track of signs also. Because remember, when I take an edge, each edge comes with an orientation. So if I have an edge going the other way, they're going to overlap on -1. If they're both going the same way, the way they overlap, that's a +1. Then I can form what's called the mesh matrix, which is the meshes of all the different loops on here. Take a basis for it, that's a basis for the cycles, and then form that mesh matrix. Notice this mesh matrix may be a lot smaller than the matrices that you form from the edges or the vertices, because there may be very few cycles. Sometimes this is a much more convenient matrix to work with. Anyway, that's what's called the mesh matrix. Okay. Now the mesh matrix actually has a formula. It can be written as a product of an inclusion matrix that we talked about a few minutes ago times its transpose, actually. So that's a fact of linear algebra, that there is a way of writing this. There's a similar fact for the Kirchhoff matrix, that it can be written as a product of a matrix times its transpose. Anyway, the mesh matrix has a nice linear algebra factorization, which we're going to use. And now the claim is that I could also get the exterior algebra version out of this. In other words, I can form a wedge product of these cycles, and I can again write down an exterior algebra element that gives me all the spanning trees formed out of the mesh matrix instead of out of all the chains, all the edges, and so on. So there's two different exterior algebras come floating in here. One is an exterior algebra on the edges. The other is an exterior algebra on the cycles. But I can get the listing of the spanning trees either way out of this stuff. Okay. There is a difference between them, which Ed and I were just discussing, which is in the issue of signs. The signs are a little bit different depending upon which matrix or which exterior algebra you use to enumerate the spanning trees. When you enumerate them using the edges, which I spent most of the time, the first 40 minutes on, 50 minutes on here, you get them counted +1. Actually, the signs work out to always be +1. When you use the mesh matrix, there's another sign that comes in, and some of them are listed with +1s and some of them are listed with -1s, depending upon an orientation issue. There's an orientation associated to the choice, and that determines a sign, and that comes in. So the formulas are not the listing of the two different exterior algebra ways of enumerating the trees are not identical in terms of sign, interestingly, actually. Anyway, okay. So all of this connects up to various other classical subjects, which I could mention here. So they've already been implicit in some of what I've said. But one is that there is the number of spanning trees. There's actually an algorithm for computing it by deleting and contracting a graph into pieces. Deleting means you delete an edge. Contracting means you pull in it on an edge. So you can produce graphs in two different ways out of a given graph and a given edge, either by deleting the edge or by shrinking in the edge. And then there are formulas that relate the number of spanning trees to what you get from those two graphs that you would generate by removing an edge in either way, in either two-way. And that's similar to what's happening here at the exterior algebra level also. That's paralleled by that here. So anyway, that provides a motivation for the what's called the Kirchhoff Laplacian, which is a matrix that gives you the two determinant gives you the number of spanning trees, actually. And then the well-known theorem is that you can get the number of spanning trees from the determinant of a certain matrix. This matrix is obtained from from keeping track of the incidence matrix of which matrices that keep track of how edges meet vertices, and from that you can get this Kirchhoff Laplacian and get it from the determinant that you get from that. You get the number of spanning trees. And these theorems that I'm describing today are attempts to organize this in terms of an exterior algebra language so that you get not just a number, but actually the listing of them completely also. Okay, now let me see if I have what I have time for here. Okay, so this is a description of what the classical Kirchhoff Laplacian is over here. That if you have vertices and edges over here in a graph, you can talk about when they're adjacent, if there's an edge with those endpoints, and the degree of a vertex is the number of edges adjacent to it. And then the Kirchhoff Laplacian matrix is an n by n matrix defined by the diagonal entries are the degrees of the vertices, and the off-diagonal entries record whether or not there's an edge connecting up two vertices or not. So you put in a -1 if there is an edge, and then you get this matrix over here. And from this matrix, you can calculate the number of spanning trees. Well, you could also do this with weights, which I won't bother with over here. I think I'll skip this over here. Okay. Okay, and we could also study the eigenvalues, but as I said, we're not going to be discussing today again here. And this Kirchhoff Laplacian can also be written as a certain matrix that describes how the things fit together times its transpose, actually, and one takes advantage of that in studying it. Okay. All right. Okay. Okay, and then you take the matrix tree, the classical matrix tree theorem involving the Kirchhoff Laplacian involves enumerating the number of spanning trees. And what you do is if you remove a row and a column, then you take the determinant of the minor of what's left, that minor, and that gives you the number of spanning trees of the graph, which turns out to be the same information that you get from the determinant of the mesh matrix as well. I should mention that these both the Kirchhoff Laplacian and the matrix tree theorem and the mesh matrix both generalize the cell complexes, but the story with cell complexes is more complicated because you have to count the spanning trees with a certain multiplicity, actually, which reflects the homology of a certain space that you construct. So it's more complicated, the whole setup, but it's of interest to carry that out as well. And so parts of this we've done for cell complexes. Okay. So in the proofs of these things, one uses the Cauchy-Binet theorem, which is a theorem that allows you to compute the determinant of a product of two matrices in terms of components of them or minors of them. And we use that over here in relating these various things to each other, but I'm not going to go through that linear algebra, I think, now, since I'm not focusing today on the linear algebra. Okay. Okay. All right. So I think that's what I'm going to say about this. As I say, there are, and the same theory works for graphs with weights as well. You can also in more complicated ways study graphs that have other kinds of weights on vertices and so on, this directly works for graphs with weighted edges with exactly the same kind of formalism as well. And as I say, it has an analogs for higher dimensions also, but with more complicated coefficients coming in. Fortunately, in the case of graphs, you measure the trees just with +1 in the case of the Kirchhoff matrix, or plus or -1 in the case of the Trent matrix. And for cell complexes, it gets more complicated. There's more numbers that come into the calculation. Okay, I think that's it. And perhaps at some future date, I'll talk about the higher dimensional cells and there's a lot of interest in higher dimensional cell complexes and repeating some of the questions that have intrigued people about graphs. For example, there are people that are studying questions like the notion of expanders for cell complexes rather than just for graphs, and all kinds of eigenvalue questions and so on you could study for cell complexes as well. And naturally, since we are topologists, we're interested in generalizing from the one-dimensional case to the n-dimensional case as well, since we started as topologists, wandered into this. Okay, I think that's all I'm going to say today. Thank you for your attention.